Demo latency is a lie. P95 is what users feel. Load test your LLM stack before production does it for you. This is the setup you'll be able to run after this, which simulates realistic prompts under load and reports 95th percentile response time along with costs. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Users notice slow tails more than averages. A demo that returns in 1 second, but occasionally spikes to 10 seconds, still feels slow. P95, pronounced P95, is the response time below which 95% of requests finish. Measuring that tail helps you avoid sudden user frustration and hidden budget surprises. Today, we ground that problem in a practical workflow. Simulate traffic against your LLM endpoint. Read live stats from a local Locust controller. Compute P95 and estimate token cost so you can trade latency against budget. At a high level, this is load testing with 2 outcomes. First, you get tail latency numbers that match what users experience. Second, you get a simple cost projection by combining request counts with tokens per call. Strengths are realism and quick feedback. Weaknesses are that a toy test does not fully replace production traffic patterns, but it surfaces rate limits and queuing fast. We will build a few tiny scripts that talk to a running Locust web UI. You do not need to write a full load test file here. Instead, we will query Locust for readiness, start short test bursts, read the aggregated stats for P95, and project cost from requests and tokens. That keeps the entry barrier low and focuses on the metrics that actually matter. Now, we'll check that the Locust controller is ready. This snippet confirms Locust is reachable and ready by querying its REST API for status. It imports requests and defines base as the local Locust web address. The call requests.get to /stats requests returns live JSON statistics from Locust's web server. The variable st extracts the state value, which typically reads stopped, spawning, running, or stopping, depending on the scheduler. Printing state equals st gives you a quick readiness check before you send load, preventing confusing results from issuing control commands to a server that isn't prepared. A clear state readout matters because starting from a known baseline avoids misleading metrics. Next, we'll start a short burst of traffic to the LLM endpoint through Locust. This example triggers a brief Locust run to create traffic against your LLM endpoint. It first posts to reset, so old statistics don't contaminate new measurements. The variable T0 captures a timestamp. Then a post to /swarm with user count and spawn rate starts generating requests. A short sleep holds the load for a few seconds, and a post to /stop ends the run. The final print shows the actual elapsed time, confirming the duration you exercised the system. Increasing user count or spawn rate intensifies concurrency and can surface throttling or queuing sooner. Decreasing them lowers contention and may hide tail issues. Now, we'll pull aggregated metrics and compute the P95 latency. This code reads Locust's aggregated statistics and derives a P95 latency figure. It requests stats requests, which returns a list of per endpoint records inside the variable stats. The variable P95 takes the maximum response time percentile 95 across endpoints to reflect the worst tail among your routes. If stats are empty, it safely falls back to 0, so the print is stable. Printing P95 aligns with tail latency you'll track in production to understand user-facing slowdowns. Higher concurrency or tighter rate limits generally push P95 up by increasing queuing delays. Lighter load typically lowers P95. Next, we'll estimate cost from request volume and tokens per call. This snippet estimates dollar cost by combining Locust's request count with a tokens per request model. It fetches /stats requests and sums num requests into the variable rex. The variable TPR represents average tokens per LLM call, including prompts and completions, while PPK sets price per 1,000 tokens. The variable cost multiplies request volume by tokens and price, normalizing by 1,000 for unit conversion. Then prints cost USD for a quick budget view. Increasing TPR or PPK raises cost linearly. Reducing them lowers the projection. This helps you judge whether a target throughput fits your latency and budget constraints. Finally, we'll compare light and heavy runs to reveal tail behavior. This example contrasts tail latency at light versus heavy load using Locust's REST API. It resets statistics, then loops over two user count values, posting to Slurm with spawn rate equal to user count for a simple shape. After a short sleep to accumulate samples, it fetches JSON from /stats requests and stops the swarm. The Lambda P95 extracts response time percentile 95, and the final print shows the difference between heavy and light runs. Raising user count increases concurrent demand, which commonly exposes throttling and queuing, widening the P95 gap. A larger P95 spike signals a scaling or rate limit issue that merits investigation. To map this toy flow to a real system, run the same checks against a staging gateway that mirrors production routing. Use representative prompts and lengths so tokens per request match real traffic. Store the P95 and cost numbers over several runs to spot variability rather than trusting a single sample. Recap. This is a quick way to measure the 95th percentile latency and a token-based cost projection using Locust's API. Use it when you want early signals about queuing, throttles, and surprise bills before release. Caveat: synthetic bursts reveal many issues, but cannot fully replace long-term production observability. Next step, run the heavy versus light loop across more user counts and tune spawn rate so you can find the knee where P95 jumps. Then pick an operational throughput below that knee. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.